So welcome everyone to session 3. We have learned so far the basics, or actually the terminologies and basics of machine learning, and also we learned about the branches and the applications that can be done with machine learning. We learned about the neural network and also the linear regression and the perceptron algorithm. We learned about the gradient descent, which is the backbone of backpropagation, which is the basic method for training and learning in your network. Now this session is about some challenges in training and also fitting either neural network model or any machine learning model. Actually, we will talk about what is called bias-variance trade-off. The idea here is to learn how to organize your training data, how to build a pipeline for training, and when to basically stop the training, what are the criteria to stop the training, and also to accept the model. So the central challenge in machine learning is that our algorithm must perform well on new, unseen, or unobserved data sets. Because the goal of machine learning is to perform tasks in real life. So not only using our training data, then we get good performance on the training data, then the project is finished or everything finished. No, we are taking the training data to train a model and this use the model in real life. So for example, we take historical data of self-driving cars where humans are first driving, and we are recording the scenes, and we are also recording the human action. And then we train models to fit this data set. But this is one step. The second step now is to put this model on real scenario, driving real car. Then there the model should perform well as well. So the ability to perform well on unobserved or actually unseen inputs, we call generalization of the model. So if the model is generalized, that means it can perform as good as basically it can perform on unobserved data as same as on observed data, or similar or close to. So the optimization problem is the minimization process to what is called training error. So we have training error, which is the error on training data or training sets. And once we do optimization, once we do gradient descent, we are actually minimizing that training error. We are minimizing the error on the training data sets. What separates machine learning from optimization is actually the generalization error or the test error, which is basically the error or the cost on the test set. So test set is a data set that is not involved in the optimization. We'll see that it is not involved in the gradient descent. It is not involved in estimating the cost during the gradient descent. It's an extra data set. It's called out of sample also. And what is important in machine learning is not only the training set error or the training error, but also the generalization error or the test error. So we need to minimize both at the end. So for example, let's talk about training versus testing. We have this red point that we have seen before for the linear regression, and these are the training points. Testing points here are in yellow. So this testing point will not be considered in finding the best line here. Only the red points are considered there. So for example, the training error or the training mean square error here is a sum of basically the squares here of the error. And here we have the x-train. So the x-train means that all the red points here, and the y-train is their y values. And that will be our training error. And the test error is basically the same function, of course, but now over the test samples are here in yellow. So the objective basically of machine learning is first minimizing the training error. Of course, this is what we do with optimization, but also to make the gap between the training and testing error as small as possible. So these two factors correspond to two central basically challenges in machine learning. It's called underfitting and overfitting. So overfitting means that we have really very low training error, but we have high test error. That means we overfitted the data. Underfitting means basically we both are high, so the training error is high itself and also the testing error. So this is again, underfitting occurs when the model is not able to obtain sufficiently low error value on the training set. Overfitting occurs when the gap between the training error and test error is too large. That means the training error could be very small, but the test error is high. Capacity, which is also important, is it's the ability to fit a wide variety of functions. So the higher the capacity is, so actually the model with low capacity may struggle to fit the data. So we'll see later if we end up with underfitting, that means we have low capacity. What does low capacity means when it comes to neural network? That means we have low number of neurons. We looked at the exclusive or function or example. We said with one neuron we cannot fit that model, which means we have low capacity there. We need to increase the capacity by adding other neurons. And if we increase the capacity, we add too many neurons, we might end up with high capacity, which would lead to overfitting, because there we would overfit the data set. We will get very low training error, which would be 0. But that basically we get which could lead actually to high testing error. And this is what is the overfitting. So here basically we see the difference between fitting and overfitting, or actually basically here we have a line which is of course has lower capacity than a polynomial model, which is high order model, nonlinear model. So line of course has here an error of 3.6, the mean square error 3.6. The polynomial error has here 1.6, which is lower, because here you can see with polynomial we can actually move through the points and along the point, not only have the best line. Now, if we look only at the training error, would say okay, I think this model is better because it's the training error here is much lower. So we want to select this model because it performs better on the training set. Now the problem is when we try now to do the testing errors, which I will go back there, but I want to show you here. If now we have new points there that are coming, and we apply this function, we can see that these are unseen points. If we look here, we can see that with this polynomial model, we actually overfitted the data, because here the training error is good, but the testing error is very bad. This one comes to, this is basically the idea of overfitting. But the linear model, it has a lower capacity, it had a higher training error, but the testing error actually is basically are very close to the training error. In this case, we don't select this model, we don't select the polynomial, because it has the gap between training and testing is high, although that the training performance is, or training cost is low. But we would select the linear one because the gap is small between training and testing. That means we can trust it more, because although the error is not that low, but we know that it's stable. So this is actually nothing with that for what I said, but here, for example, when it said that the linear model doesn't fit the data very well, and therefore it's said to have a higher bias. So because the error is high, so the low bias, that means we can fit to 0 error, let's say, or close to 0. But if we don't end up at the 0 error, that means we have a bias from 0. And this is why the linear model has a higher bias. And for example here, for the polynomial model, we can see that polynomial model would lead to overfitting, which means it's not generalizing, it has a lower generalization. and it has actually high variance error here, you can see. So the linear model, low capacity, but it had a higher bias because it's actually the error is not zero. The polynomial model is actually has a low bias because in the training set it was very low. But we can see that if we change the data slightly, the shape of the curve will look very different and the error will swing widely. Therefore, we call this model that has a high variance. So that because it can change rapidly if we add a new point. So the machine learning is not about perfection. So it's not about having zero error, as I said. We need to have a trade-off. We need to have basically, first of all, high variance is not good. Bias is okay because if we have a bias, we can know that the system, for example, has 70% accuracy, and this don't change when it comes to new data sets. So we know the limit of that system. But the challenge would be if we think that the system has 90% accuracy, but once we test it with a new data set, it gives us 10% accuracy, which is very low, which is and also very risky, of course. So how to deal with now this trade-off and how to test if the model has good generalization or not. If we have a data set, so we get data set, for example, from clients, from people who want from us to train or develop a machine learning model, what we need to do is to divide this data set first into three parts. The training set, which should be basically the biggest set here, is typically 60% of your data. So this used to train the machine learning. So this would be actually involved in the basically the backpropagation or the gradient descent. Validation set is something in between. The validation set is called also the development set. This is usually 20% of your data. It is not used during the training, but it's used to test the quality of the training model during the training. So what we will see later that, of course, when it comes to neural network, we don't know what is the optimum capacity. We don't know what is the optimum. There's no rule of thumb of how many neurons can I choose, how many, let's say, layers I want to choose. So what optimization method to choose. So these are hyperparameters to select, and these are model. So we need model selection process. And the idea of basically validation set, and here we have 60% and 20% data set, is we need to do model selection before going into the test set. For example, I train 60% of my data using model A. Then I test on the validation set and I record 70% accuracy. Then I do again training on the 60% of the data with model B, which has different parameters, different number of neurons and so on. And I test on this 20% and I get 90% accuracy. Now I select then the 90% accuracy because it's a better model. It has a better validation error. And so now I can trust it more. Now just the last step to really be sure about this model, we can test it now on the test set. So that is validation set is a test set that is involved in the model selection, but test set is basically really the out of sample. So it was not involved at all in the training. Another way is to do basically the k-fault classification. Now here, when it comes to k-fault cross-validation, the test set stays out of this scope. So at 20%, this is out of the scope. Now we take the training set, which now, or actually, yeah, this one now includes the training and validation as we see later. We have k-fault. Let's say here we have 4 faults optimized or actually learning or validation. So the idea was 4 faults. That means we need to now to divide our training set to 4 sets, like here 1, 2, 3, 4. Then we do 4 experiments, which means we train on 3 sets and we to validate on the one that is left out, which is now here test 1 set. Then here, the second experiment, we train on this 3 and we test on this. Then here we train on this 3 and we test on this. Then here we train on this 3 and we test on the last one here. Then basically the validation error of that model would be the average error along these 4 experiments. Okay, so the sum of error divided by the number of faults, which means 4. The reason here, first of all, we want to test the generalization power of this model by not only testing it on one validation set, by changing the validation set. For example, training on the 3, validate on that, and now training on the 3 and validate on that. Just a general example, let's say we need to train against self-driving car. We have training set, we divided to 4 faults. One fault includes basically data set of driving in a clear, very perfect environments, and also during the day. So it's also very good illumination. And so basically, this is one set. The second set would be training, or actually data set that includes driving at night, but also perfect weather. The next one would be basically driving, let's say, day, but with snow. This one is driving at night with snowing weather. So the first thing, we can actually train on these 3 and see if the system would actually perform well on perfect weather. If it is very good model, if it could correctly generalize, then using these 3 conditions would drive correctly on clear weather daytime. Here, for example, it's something else. Here we train on day clear, day snow, night snow, and we test basically on night clear. Here we have day clear, night clear, day we test on day snow, and we train on basically night snow, and so on. So this is basically the idea of generalization, and is this model really smart to generalize on unseen data, unseen conditions? This is why cross-validation is very powerful here. So how to use now the idea of validation errors, and also how to do this, the bias-variance trade-off. So in machine learning, we said that the error is made by your model is a sum of 3 kinds of errors. We have the bias error, the variance error, and we have here basically an reducible error, the third one. So this is our progress of the error that we have seen also in the neural network before. We have the training error in blue, which means the error on the training data set. We have the validation error here, which could be, if you're talking about the cross-validation, it could be this value there. Now, at the beginning, while the model is training, here at the very beginning, we have very high bias because we have very high error at the both actually validation and testing, or training, sorry. The longer or the more iterations we have, the lower this error becomes. We still basically have kind of high bias, but here we still basically start to reduce it. What is good until now is, okay, the validation is a bit bigger than the training error, but it's not that big, first of all, and the gap is kind of stable. So this place here, it kind of has minimum training error and the minimum validation error, and the difference between them is not that high. But if we continue training, we can see now we are getting to high variance place, or high variance region, where we start to get very low training error, but the validation error started to raise. And this is the overfitting area. This is the underfitting area. This is what we are looking for. So the idea of here, basically, you start training your model, and once you start to see divergence between training and validation error, you need to stop, and you need to select here the best, which means the minimum validation at minimum training and the smallest gap between them. So this is what, for example, that we have seen before. So how to detect the high bias problem. We have high training error, and the validation error is similar in magnitude to the training error, which means we are here. So basically, we have high training error, and also we have high bias error at the same, high variance, high validation error at the same time. And this is basically how to detect the high variance. We have low training error, but we have very high validation error, which is in this case, and also you can see it in this case here. So what is the training approach then to overcome such a problem? We start training. We have high training error. If yes, then that means we are still in the high bias. What to do? Train longer, more iterations, or train more complex model, or obtain more features if we are doing feature extraction. Deep learning, as I said, it's called end-to-end learning. That means it should extract the features automatically, but if you want to add features, you can do that. Degrees, regularization, which I will talk about that later. New model architecture, so just to add new model. This is basically if we don't, if we are at the underfitting, so we cannot we cannot actually improve the performance. If the high training is not high, or the training error is not high, we now need to check the cross-validation error. If it is high, that means we are in overfitting. That means we need to either decrease, that means also we have now high complex model or high capacity model, which means we need to decrease the number of features to decrease the capacity. We need to add a smaller model or add a new model which has a lower capacity, or which means also we need more training data. Why we need more training data? Again, coming back to this example, let's say we trained only on daytime, snow and clear, but on daytime. We never trained on light, or actually in dark, sorry. So if I'm only training on daytime and I don't have data set for dark, then my test set is actually on basically dark or night. Then here the validation error would be very high. And I need to have more data for the training set. So I need to also include now some night condition and also snow at night condition under the training set. So this is what we mean by adding or training more data. Also, if we have too many features, that also could lead to overfitting. That means we need to decrease the number of features. As I said, this is with deep learning is not that important, because deep learning does feature selection and feature extraction. If we have lower, which means we have low training error, we have low validation error, and then we are done. That is the best system we can get. So this is in general the bias variance trade-off and the cross-validation. They are very important to train machine learning models in general and deep learning models also. The next session we'll talk about now backpropagation algorithm, which is the main algorithm to train neural network.